Let's have a look on the redox zonation of typical well site in Berlin. You have here in this figure on the left side the lake where the water is infiltrating, and you have the production well where the water is abstracted. And from a project carried out in 2003 called Nasri, we know that we have a horizontal redox sequence from oxic to iron reducing conditions in the aquifer, and increasing thicknesses of the oxic and suboxic zones towards the production well. And in case of operating the well, we have a mixing of water with different redox states in the production well, which can cause iron precipitation and the clogging of the wells. Our research objectives focus on the assessment of the impacts of the well operation on the forming of these iron deposits in the drinking water wells. Therefore, we differentiate between a single well operation and well field operation. So single well operation can cause a reaeration and entrapment of air caused by the fluctuating water table due to the well operation. And as well, it could happen that you have a mixing of aerobic bank filtrate or artificial recharged water and anaerobic groundwater. So from different sides of the well. The well field operation can cause a mixing of waters with different redox states by operating a neighboring well. So the well could age and get clogged only by operating a neighboring well, not the well itself. So our first approach was statistical analysis of the hydrochemical and operational parameter of these wells in all these 800 wells. So first we did a classification of the clogging related to TV camera inspections we have from the wells. And in the figure we see that every row represents a well field, a Berlin well field, and we see that there are quite big differences. So there are some well fields which are stronger affected by clogging than others. If we take a look on the operational parameter, it is obvious that the clogging intensity correlates with high pump switching rates. If we switch the well often, we have more intense clogging of the well. As well, the operating hours, the mean operating monthly hours, are also correlating with the intensity of clogging. So it's the operating hours. It's also stands for the mean discharge rate of the wells. They are calculated. The discharge rates are calculated from the operational hours. So we have the clogging intensity is associated with the discharge rate as well. So that's not surprising. If we then take a look at the hydrochemical parameter, especially on the redox sensitive parameter, like iron and as well as nitrate, oxygen, and the redox potential. I only shown iron and nitrate because the redox potential and the oxygen data were not really reliable and suitable for our statistical analysis due to the sampling method. But if we take a look on the iron concentrations, we see in the first moment, surprisingly, that high or intense clogging correlates with low iron concentrations. But there is a reason for that. So it could be that the iron is already removed from the water before we take the sample. And the nitrate, when we have high concentrations compared to other concentrations in the well, high concentration of nitrates in the abstracted water, then we have also intense clogging. So to close this gap that we don't know what is about the redox potential and the oxygen, we perform a hydrochemical monitoring of chosen wells. So we choose 22 wells from the 800, which are more or less representative for those. And we observed different variations. First, on the first side, we just have short-term variations in the hydrochemical, in the hydrochemistry. So we did a raw water sampling instantly to switching on the pump. And we see that in the first minutes after switching on the pump, oxygen is disappearing in the most wells. There are only some few few wells which are showing oxygen after half an hour, but it could also be that there are some damage in the construction of the well itself. And if we take a look on the redox potential, we see that we have stable conditions after nearly 30 minutes or 1 hour. Then furthermore, we observed midterm variations of the hydrochemistry, which are controlled by the well field operation and expressed by variations of inflow rates from, for example, groundwater and bank filtrate. And we also observed long-term variations, which are controlled by mostly by the seasonal effects, and therefore by changing temperatures and therefore changing consumption rates during the infiltration and the flow from the surface water to the abstracting wells. So therefore we have to take a closer look on the mixing processes and on the location where the mixing takes place. And we perform a depth-oriented sampling of the drinking water wells. So we took samples inside the well during the well is operating. And in the figure in the middle, it is shown the concentrations of nitrate and iron again as a function of the depth. Oxygen was also absent all over the profile, so we couldn't detect any oxygen in the well itself. But we detect in the lower part of the well, filter section of the well, we detect high concentrations of iron and low concentrations of nitrate. And in the upper section of the filter, we observed high concentration of nitrate and low concentration of iron. So the iron has to, first, this is corresponding to the redoxination outside the well. If we take a look outside the well in the aquifer, nearby, around 3 meters from the well distance, we have on the right side, we have high concentrations of oxygen in the groundwater. So, but the oxygen is disappearing on the way to the well. And so therefore we only have nitrate as oxidizing agent in the well, and oxygen is completely consumed outside the well. For a characterization of the oxygen distribution outside the well, and to study the reaeration and the air entrapment in the aquifer, we construct a transect of multi-level observation wells, and we install oxygen senders in different depth of the aquifer, as shown in the left figure. And I just want to show one example of the measurements and what we find out here. We have at the beginning, before pumping, we have certain concentration distribution of oxygen in the groundwater, and if we start pumping, we shift the oxygen and the redox zones down to just like to the depth where the filter is situated. Right? And in case of recovery, we shift it back, but there's a formation of and creation of a suboxic zone, a bigger suboxic zone in the aquifer. So we carry out quite a few of these measurements with on 3 different well sites, just to compare if it's only at one site or if if that's generally pattern. And we did different studies, different experiments. So we did short and midterm variations during the well operation. Then we just make a sequence of several switching events, so on, off of the wells. And then we just rest the well itself and operate only the neighboring well. So I will make a conclusion now in the next slides, just presenting the conclusions as a conceptual model. So we have at the beginning we have static groundwater level and conditions in the aquifer. We have only a thin oxic and suboxic zone which is created by diffusion from the unsaturated zone. We have a thick anoxic zone free of oxygen and nitrate but containing dissolved ammonium, manganese and iron. If we then start operating the well, we have a drawdown and a reaeration of the aquifer in the zone of the drawdown, and we have a mixing of these thin oxic and suboxic zones near to the well and in the well itself, and therefore precipitation of iron hydroxides. In the next step, we shut down the well pump and we have a recovery. In this recovery phase, we have an air entrapment of the bubbles, the entrapment of the air bubbles, and subsequent dissolution of these air bubbles and the oxygen by diffusion. And there could also be some mixing reactions by flowing groundwater to fill up the cone of depression, and there could also be some precipitation of iron hydroxides. If we just repeat this and just operate the well again, we have the same effect. We have a reaeration of the aquifer and the cone of drawdown. But now we have a thicker zone of oxic and suboxic zone by transversal dispersion in the aquifer. So we have a more intense mixing reaction and a more intense precipitation of iron hydroxides at the well. So then again a recovery phase, for example, and again with the dissolution of air and oxygen in the cone of depression. And then we have just like resting wells and transport only by the natural gradient, and therefore also a consumption of the oxic species in the groundwater. And at the front and at the back we have a reduction of the former oxic aquifer by anoxic water coming from flowing on this path. So if we then operate a well, for example here, a neighboring well, we have a migration of this cone, of this oxic cone through the aquifer, and we have at the front we have more or less not has to be a sharp front like it's shown here, but it could be. There we have again oxidation of the reduced aquifer, and in the back we have reduction of the oxidized aquifer. And if this front reaches the well, we have intense clogging, intense mixing reactions, and therefore a problem, a problem. Thank you for your attention.